Eh bien, bonjour à tous, merci pour votre présence. Donc aujourd'hui, on a le plaisir d'accueillir Martin Karsai, qui travaille au Department of Network et Data Science à la Central European University de Vienne, en Autriche. Martin abordera aujourd'hui des éléments, alors je vais pas vous lire le titre, mon anglais est trop terrible, mais va aborder en fait des éléments sur lesquels on a travaillé ensemble dans le cadre d'un projet ANR, l'ANR d'INET, qui a impliqué le département de Marton et le laboratoire d'IBM de l'UGA. Voilà, je te laisse la parole.
Thank you very much, Aurélie. I'm going to talk in English if you don't mind. Otherwise, it would be too entertaining if I would. I'm very, very happy to be here for several reasons. First of all, that I can continue working with my colleagues here at the University of Grenoble. And also, almost by the day, I defended my PhD here in Grenoble 15 years ago. So it was it's a nice anniversary, nice comeback. That time, the university called the University of Fourier. But yeah, many years passed then. Since then, I'm going to talk about, actually it's going to be like an advertisement talk for a project we were carrying out here in Grenoble. The first part of my talk is going to be more of a data science approach to tell you how we actually obtain the data and how we process the data and have we reconstructed temporal social networks from the data that I will explain what data is about. And the second part of the talk is going to be a modeling effort. It hasn't been published yet, but it's already in archives, so if you're interested. So in order to set a little bit the context of my talk, I'm going to talk about a social experiment that we carried out here, which was aiming actually to record the language and social network evolution of children. And why is it important? We were actually focusing mostly on preschools. And in preschool, you know that kids may come with various different socioeconomic or sociodemographic backgrounds, and also they carry different linguistic level in school, meaning that they start the initial state in terms of language is very heterogeneous in the beginning when they are age 3.5. At the same time, we also know that their language acquisition, their language development is strongly influenced by their socioeconomic status. You know that kids coming from more affluent families, they have a larger vocabulary set, they have better morphology, and so on and so forth. So this is one influencing issue or influencing character that is characterizing the language development of children. At the same time, we also know that their interaction plays a role because they talk to each other, they influence each other. Similar kids form groups, for example, in terms of different characteristics induced by homophilic preferences among them. So there must be some role of the social network behind their language evolution. The problem with this large question is that it is very difficult to observe. Actually, there is no longitudinal data that has been recorded which can follow the social network evolution and language evolution of young kids during the first 3 years of education. And also, that has been done already. Typically, they are done by questionnaires or surveys, which are very general, which provide very general information about this process. So our goal in the DLNet project, which unfortunately has been done, at least the data collection part of it, was to somehow obtain a data set that we could examine the co-evolution of language and the social network. And the motivation behind was that in the very beginning, when kids enter the preschool, they speak very different French, very different language, mostly determined by their socio-demographic background, something that they're carrying from home. And in the end of the third year, they all speak the standard French. They all speak the same language. So the question, how you could arrive from this very heterogeneous initial state to a very homogeneous output or final state as a function of the social network. So these are actually two objectives of the project. First, to obtain the data and analyze it. The second, to establish this relationship between language evolution and social network evolution. So to do that, we had to involve researchers from many different fields. the two engine of the project are actually here in the room. It's Aurélie and Jean-Pierre, who are sociolinguists, but we also had computer scientists, ethologists, and network scientists like myself on the team to carry out this project, because it turned out to be a larger challenge than we expected. The data collection actually started a year before we recorded the single record, because that was about 1 year with the ethics committee that we could carry out this project. And what we actually done, we identified, with the help of Fourier, we identified a school here in Grenoble, which had about 200 kids and their teachers and assistants. The kids were between 2 and 6 or 3 and 6 years old. And our goal was to collect their social interactions and information about their language or linguistic development over 3 years. We were collecting data for 1 week every month over 3 years. 1 week means that we had 5 morning sessions and 4 afternoon sessions, because there was no school Wednesday afternoons. So in the end, we had a very large data set where we had different channels to collect data. More practically, we collected, most importantly, the social network information of children. And what we were doing, we used the RFID tags, which is like a small device which was emitting a signal every 5 seconds, and otherwise listening to surrounding other badges or surrounding other devices around the children who was wearing it. So we stick this on the kids over the whole day, and we were recording the proximity interaction. So we recorded if they were close to each other, and depending on their orientation as well, every 5 seconds for all of the 200 children in the kindergarten. This was at the time something new, but was already somewhat standardized, because there are other data collection efforts which were using similar technology. Just to mention, for example, the sociopattern dataset. That was a sociopattern project that was carried out at ISI Torino, and earlier also in France there were similar experiments, not on children, but for example in the hospital setting. They were trying to figure out how diseases passed between staff and patients. On the other hand, what was completely new in our data collection was that we didn't only record the proximity interaction of children, but we recorded their voice. There were 2 microphones on every bench. These are directional microphones that we could identify who is speaking. So we could identify that the person who was wearing the badge was speaking, and recorded their voice for 3 years, which is a lot of data. A lot of children speaking, okay? Which is a huge challenge process, and we are still not there yet. So if you're interested in automatized transcription of training models to automatize transcription of children's speech, please contact us, because that would be great. So at the same time, we had an ethologist sitting in the room, because we needed, as I will explain later, for training purposes, rankings data. And she was using an application coming from actually animal studies to measure the orientation and the distance between children. Originally, it was developed for gorillas, if I remember correctly, but in this context, it was exactly this. Okay, so we had also Tarantus data on the side in different contexts, in control context and free playing context, coming together with our dataset. We further examined the children periodically in the beginning and the end of the school year. They were actually completing the linguistic test to see how are their standard linguistic variables evolving as a function of time. And this data that we have already about their language evolution. And we also went to the families to ask to learn about their social demographic background. So what is the education level? What is the spoken language at home? What is the living environment of the children? And so on and so forth. So these were also done as a survey with the parents in the very beginning of the experiment. Finally, we had the log from the school that we could actually learn about the ethnographic environment of children in the school. So we have these 5 data channels. Today I'm going to focus on the first one, which is social interactions. And my goal is going to be to show you how we reconstructed from these radio signals in a reliable way the social interaction, the dynamical social interaction network of the 200 children. So when you run an experiment like this, the net data that you get right away from the badges looks something like this. So these are actually records in every 5 seconds, more or less, between the children who is wearing badge and what this badge is seeing around. So actually, this is a list of IDs, badge IDs and user IDs that were detected by a badge that was worn by a given gene. And our problem, our challenge was that we had these 200 badges and we had to check pairwise each of them to see whether they mutually saw each other, and from that we could actually infer whether these kids were close enough to each other. The data what actually each badge was measuring was a badge ID, which was associated to user ID, because not a single badge was always landed to the same kid. Sometimes from day to another day, different badge was given to a kid. We had the time, which is in epoch format, and also we had a signal strength value, which told us how strong the signal that the badge is recording from other badges around. Just as an initial analysis, we looked at the distribution of the signal strength, and we found it's a very nice bimodal distribution that we could actually explain by looking a little bit further on the data, where we looked at the average and the standard deviation of these signals. And we realized that actually these two modes are corresponding to two contexts. One is that when the badges are put back in on the charging pads, and they're very close to each other. So from a behavioral point of view, it's completely useless, this part. But on the other hand, the other part, which corresponds to weaker signals, of course, these are actually the data points which were recorded when kids were in their natural habitat and they were playing and moving alongside. We could actually identify the corresponding value of the signal strength around the minus 65 dBm. That was well separating these two data clouds. Further, we were also interested in how body orientation was influencing change in the signal strength. This is because, human body is mostly water, so it is emitting radio signal very well. And we even run some experiments by using water bottles and put the badge on the water bottles and turning the water bottles left and right, just to have some controlled experiment. That we also succeed to convince kids to stand still for 10 minutes, whether side by side, face to face, or back to back. That we could actually record data points as a controlled run-through experiment for later training. And you could see that this is, for example, the face-to-face 10 centimeters, face-to-face 2 meters, 1 meter, 2 meters, face-to-face, side by side and back to back. You could see that there is a difference or dependence on the body orientation and the signal strength. We could simply characterize this by measuring the distribution of signal strength for the different orientations, and you could see that when they were face-to-face, the closest, that correspond to the strongest signal observed, and when they were back-to-back 1 meter from each other, that correspond to the least or the weakest signal, but the badges were picking up. Finally, we wanted to somehow determine what is a social interaction, what distance corresponds to a given social interaction. And we measured actually the signal strengths and the distance correlation, and we found that actually the most frequent distance is around 1.5 and 2 meters, that corresponds to about minus 80 to 83 dBm. So this was a good guess for us later on how we can differentiate between non-social interactions and social interactions. Very well. So at this point, we had a somewhat good idea of how the data looks like, but yet we didn't start anything about the reconstruction itself. The reconstruction pipeline looks something like this. We had originally the pair of We had a pair of badges. Each pair of badges, we identified the handshake pairs or sequence of handshake pairs, which we converted into a binary signal. We used some reconstruction method to fill in the missing data points that were caused by some lost packages or errors. So we could construct interactions with duration. So we arrive back to the original temporal. And I will walk you through step by step all this pipeline. The first step, let's say we have two badges. These badges are in proximity to each other. And we have what badge A was detecting, and we have what badge B was detecting. First of all, we had to match these two sequences such, because the time was synchronized, we could do that, such that the one line here corresponding to a given time corresponding to another line in the other data set, plus minus 2.5 seconds, because we measured everything every 5 seconds. So we obtain these pairs, handshake pairs of the different badges. And as you could see, these are the signal strengths for the corresponding handshake pairs, and they vary a lot in time, depending whether the kid is closer, further, or they are not playing together at all. As a second step, we just filled in the missing data points when the two badges were not seeing each other with some default value that later on we could detect that this was actually a period of no interaction. And we actually created this signal of handshake pairs. We had pairs of both directions, whether the signal was stronger than the default value, which was corresponding to no interactions, or weaker. So we could see that at this time, both of the badges detected each other. At this time, none of them detected each other. This time, one detected the other, but not the other two. Okay. So now the challenge is that if we have this handshake signal pairs, how can we convert this to a binary signal, a sequence of zeros and ones? Zeros meaning that they are not interacting. One means that they are interacting at a given time. This can be wrapped as a relatively simple classification problem. Since we have these pairs of signals, each of them are corresponding to a signal strengths. So we could simply show or correlate the two signal strengths corresponding to the same handshake. And we had the ground truth data. So we had measurements where we knew exactly that this was a social interaction. It was not a social interaction. So we could actually colorize a given point depending whether it was a real or not a real social interaction. So you could see that it is a relatively well separated point cloud. Actually, this part was corresponding to interactions, and this part, which are mostly red, are corresponding to no interaction. And we just applied the logistic regression to identify the decision surface. And we could come up with, if I remember, 77% accuracy, a good classification of a handshake pair to be correctly classified as an interaction or a non-interaction. So in the end, from this handshake pair signal, we actually received a binary signal saying that at this time there was an interaction and at this time there was not. But yet this signal is not perfect because it's possible that packages are lost, or it's possible that the humidity in the room is so large that the radio signal is disturbed simply by two kids talking and one walking in between them. Capture the signal, so there are a lot of noise in this binary signal. So we had to come up with some reconstruction model, method, that we could fill in. For example, you can see here, there are two interactions and there is one no interaction in the middle. Probably that's a missed package or missed data. Somehow we needed a reconstruction method or more than one that could correct this kind of mistakes, and we could reliably reconstruct the interactions with the duration emerging between inputs. So the simplest method, what we called reconstruction method, what we called the naive method, and this was actually the only method that has been applied to any other data set on the market at that moment, is very simple. What they say in the naive method is that if they define a window size, let's say now that window size is 1, okay? If there is one missing package between two interactions, we just bridge it. And we say that this is an interaction, okay? And you can do it with a larger window size, 2, 3, 4, and so on. So using this method and our ground truth, you could arrive to pretty good accuracy, 80%, okay? But this is not good enough. So we went a little bit further and we applied another method which was based on a hidden Markov model, where we could consider interaction data prior to the data point that we wanted to actually infer. So this was relying a little bit on a short-term memory on the past in order to predict if that missing point is really a missing point or it is actually just a lost package. Using this method, we could improve a little bit our performance to 84%. And finally, we applied a third method, which was a bidirectional long short-term memory model, LSTM, bi-LSTM model, where we were not only considering information from the past, but we also considered from the future. So it means that actually the model was predicting not only from the actual and the previous time steps, but also there's a symmetric envelope around the given point. Plus it was bidirectional, meaning that we run the model in one way and then we run the model forward. Okay? So this way, we could go up with a binary signal up to 88% of accuracy. And we were still thinking, how can we do it even better? And we actually used them in two other versions of the bi-LSTM model. In this case, with 88% accuracy, we used the binary signal. Then we had another version where we didn't feed in the binary signal, but we fed in the probability that was provided by the logistic regression classification. And in the third case, where we don't care about classification and we fed directly the signal strengths, what we obtained from the package. What turned out is that our last solution was the best, meaning that whole classification was for nothing. But we learned that actually it was not so good. We could actually reach around 90% accuracy, even further, on average around 90% accuracy with this RSSI bi-LSTM model. Here you can see that as a function of window size, the naive model and the Markov chain actually couldn't reach very high. It could go up to like 83%, but the bi-LSTM models were going very high. And this is actually just the distribution of the tested accuracy, which is on average was going up to 90%. So now we have a reliable method that we can use to reconstruct this temporal network. We could actually fill in these lost packages and we could assign duration to each interaction. So we know the beginning of an interaction, the end of an interaction for all 200 kids for all 3 years of data collection. Nice. How can we see, or how can we check that this all makes sense? Because on the ground, you know, data processing level, it all makes sense because we have this fancy accuracy volume. But from the network science point of view, we didn't have any proof or any guess whether this all is just not, you know, an engineering exercise. So we went back to the data, to the reconstructed data, and first we measured the rate of interactions as a function of time. What we found is that the unreconstructed network had the largest rate of interactions per minute. Okay? And as we are improving our interaction method, this interaction per minute rate was actually decreasing and decreasing. So the lowest rate of interaction was produced by the RSSI bi-LSTM model because that was merging the largest number of packages into a single interaction with longer duration. Okay? At the same time, we could also look for characteristics which describe the dynamics. For example, the interval time distribution. Interval time means the time between two consecutive interactions of a child. Okay? This typically appears in any human behavior actually as a power law distribution. That's what's called the bursty phenomenon. And this was also expected here. And as you could see, quite robustly, it appears as a, well, I wouldn't call it as a power law distribution, but I would call it as a broad distribution, ranging over several orders of magnitudes in seconds, with a characteristic exponent that was very well matching an exponent that has been measured 5 years earlier in other data sets, the sociopattern data. So this was already something very promising that we are doing something good. At the same time, the same could be told about the duration. So we simply measured the reconstructed duration of interactions. So how long kids were interacting with each other, and look at the distribution of it. It's again something broad. It's almost like power law. There is a fraction of it. Which is closely a power law, can be characterized by exponent matching the literature value. So this way we could somehow validate a reconstruction from a network science point of view. And this is actually an aggregated network of 1 week. You could immediately see that the 7 colors are actually coming as a result of a community detection method corresponding to the 7 classes in the school. You can see that the largest dots, darker ones, they are the teachers actually in the classroom. The dots between the assistants shared between different classes. So all in all, the network reconstruction made sense. Okay. Do you have any question about this part of it? Yeah.
We understand when you say that the best results you obtain when you direction and long-term memory model directly on the SI information.
Yes. Yeah. So yes. So here, what I told that the input of this STM model, bidirectional STM model, is the binary signal. Okay. So this we are giving a signal labeled pairs, where the signal is 0. Okay. And the label is it an interaction or non-interaction coming from the ground. So now imagine that we are not giving zeros and ones, but we are giving the signal strength what we measured with the patch. Okay, so without a complete classification skipped. Okay, directly feeding the original signal, and that was giving the best result for reconstruction.
For the ground truth, were able to report all the predictions or?
Oh no, it was an observational approach.
Yes.
So they were.
So
So the ethologist was following pairs of children for 30 minutes, okay, and do it for many pairs of children. So it was not like because it's cognitively impossible that you can follow alone complete class. It was just observing 2 kids, how they move and interact with each other for 30 minutes, and then move to another.
it was sufficient. It was providing enough labels to train the models.
Yeah, so there were a large number of pairs, but they were not more than 2 kids, how to say, observed at the same time. All right, so we have this nice temporal network that we reconstructed. Now, the question, what can we do with this? The original goal of the DLNet project was to use this reconstructed temporal network and couple this with the linguistic information coming from the voice data or coming from the questionnaires. From the voice, since it is not processed yet, we could, or just I think a couple of hours has been processed yet, we could not use, but with the questionnaires, we are actually building our project where we are looking for this multidimensional homophilia between children to understand what are their individual characteristics that determine the most whether they build a social interaction or not. Are they similar in terms of linguistic development, in terms of socioeconomic status, in terms of gender, and so on and so forth, in 2 different contexts, whether when they are in the classroom or when they are mixing on the schoolyard during free play sessions. Okay. At the same time, with some other colleagues, we started to move in another direction, entirely using only the temporal network dataset to run a study on how the dynamics of social groups are evolving as a function of time and how can we model it. Actually, we got lucky because, as I said, we were not the only one who were collecting similar datasets. There is another dataset which was collected at the Danish Technical University by Suna Lehmann and his team. It's a very large dataset, and it is shared openly. If you want, you can download 1 year, I think, no, 4 weeks of data. This is 700 freshman students at the university who were given a mobile phone, okay, when they entered the university, and well, the pay of this, the benefit was that they could keep this mobile phone in the end of the study. How to say, the price they paid is their life, pretty much, because they recorded everything about them. So not only location, but communication, social media. There were psychological tests, sociology tests. So this is it's a very large study. If you are interested in behavior analysis, it is a goldmine. They are not only recording locations at the university, but all around Denmark. So you can match home locations and everything what you need. Of course, the shared data is aggregated at some level, so you cannot actually identify home locations. Other sensitive information, but it's a very nice data set. It is recorded. The subset what we were using is a Bluetooth signal strength data set. It is again a proximity data set, but not with radio signal, but with Bluetooth, and it was recorded with aggregated up to 5 meters. But we have these 700 university students interaction, temporal network interaction, measured in different contexts, whether they're in the classroom, they are at the university, but not in a classroom, or they are not at the university. It's different. At the same time, we also published our data. So if you're interested in the data set, you can check this paper in Scientific Data. So this was our other data set we were using for this study, which was very, very cool because the first one is a very different age group, right? So these are 18 to 23, and this is from 3 to 6. Yet the data sets are comparable, and we could draw or not conclusions about similarities or dissimilarities between group dynamics of young adults or very small children. Well, this project is about social groups and their dynamics. So how could we extract social groups from this data? We did a very simple approach. It's a snapshot approach that we cut the time into equal size windows, and we aggregated all the interactions within a window. And we said that nodes are in a group interaction if they form a fully connected clip. Okay? If all the n nodes detect the other n minus 1. Okay? So we were looking for clicks like here to identify group interaction. And we were not the first one who were coming with this concept. Other studies were using other data sets to look for group dynamics. Especially, they were looking for what is the size of these groups that they could identify this way in RFID studies or Bluetooth studies or Wi-Fi studies. And all in all, what came out that all of these distributions indicate that there is a variance of group size. The size, the maximum size of groups depends strongly on the context. For example, here at the university residence, I think Stanford, it goes even up to 14, while you could observe, or for example, in a congress, you can have groups larger than 20-something, because people are forming larger groups. But for example, in a school in Lyon, the maximum group size was 4. So it strongly depends on the context, how large social groups people form spontaneously. So this is the first thing that we measured as well. We measured the group size distribution for the university and the preschool setting. For the university, we had these 3 contexts that I already mentioned, whether in class, out of class, or weekend, which means that they are not at the university at all. And what we observed that in class, people are forming larger groups. And this is true also for the preschool. And this is because of the restrictive context, because the student, the teacher is telling you to sit around the table, for example, or they are sitting close together in a workshop and trying to work together. While when they are free to choose who to interact with, actually they are forming smaller social groups. And this is consistent between out of class and so on the other hand, main question, so it was established, it was matching the literature so far, but our main question was that, all right, we observe these groups, but how these groups have always a function of time, how people leave, how people join a group, how people fall apart, or groups fall apart or merge with each other. So how do people move across groups of various size, and how do groups form, evolve, and break up? First of all, we had to, again, conceptualize what we really want to see. What is the group dynamic, how we could observe, define the dynamics of it. And we took 2 different approaches. One approach is from an individual point of view. So is that from the point of an individual, there is a group that you are involved in, and you don't really have to leave the group, but the group is changing because some other people come in, some other people go out. Okay, so there is an individualized concept of group dynamics. This is the first part, and later on I will talk about from the group point of view. So if you measure from the individual point of view, the conditional probability to find a node, a person at a given time in a size, group size k, and in time +1 at k prime, you can actually draw up a matrix like this. This tells you that a person who was at group 17, what's the probability at time t? What is the probability that time t +1 is going to be in group 1, group 2, size 1, size 2, size 3, size 17, okay? Or even larger. So it means that whether individuals are moving to smaller or to larger groups. Okay, and what you can see here is that for smaller groups, the most likely is that you are not changing the group size. Okay, if you are in a group size 2, probably you are going to stay in the next time step in a group size 2. On the other hand, you can see this down band of this distribution. You can see that as we are increasing the group size, people start to move to larger groups and smaller groups, and for very large sizes, actually groups are only moving towards smaller groups. Okay, so there is a strong diagonal indicating the preference to stay in the group or interact with the same size, but as the group is growing larger, groups are actually melting and they become smaller. This is actually very consistent around the different contexts. We could find the same at the university, at the different contexts, out of class, weekend, and in class, and also in the preschool. That this distribution of the K is shifting as we are going from smaller to larger. So this is from the individual point of view. Now, what the question, yes, we also measured the group duration to describe that dynamic. So how long exactly the same click survives as a function of time? How long the group survives as a function of time? And we found that these are all distributed in the different contexts as a broad distribution. Again, to be bold to say that it's a power law because it has bumps and exponential cutoffs and all these things. I spent several years of my life to characterize distributions like this. But you could characterize them with an exponent, which is well fitting at least one segment of their distribution, and you could see that these are varying actually between 1.7 and 2.2. Again, something matching the literature. Now the question is, we are done with the individual point of view. Let's take a point of view from the group. So if you're a group, let's say that you are like a water drop on a surface, okay? And this surface is not plain, but it has some bending, and the water drops are going down. These water drops, because of the capillary force, they are going to merge and they are going to split. And this is something what goes on in a social setting. There are social groups which join each other. There are social groups which are breaking apart. So now the question is, how can we measure this in the microscope? And what we came up might not be the most intuitive way of measuring, but I hope I will be able to explain to you. Let's assume that you are in a group of size 2, okay? You arrive to this group, so there was something before, and you are going to go somewhere, there's going to be something else. So we measured the probability that the largest group that consists of the actual group that was before, what was the size of it? Okay? But it has to be smaller because it had to emerge. From different groups in order to arrive to a given size. And again, after this group is dissolved, it is going to fall apart to smaller groups. What is the size, the largest size, largest subgroup, it is going to fall. Okay? So for K equal 2, the disaggregation is obvious because from a 2-size group, the largest subgroup that you can fall apart is 1. Right? So this is probability 1. The largest group that you can arrive from to group size 2 is going to be 1 as well. So again, probability 1. You can do it for group size 3. Now it's distributed between 1 and 2 because you can arrive to group size 3 from merging the one group with 2 other one groups, or you can merge size 2 with a one group. So this is why you have already 2 values in your distribution. You can actually do it for any group size. Now, what you observe is something very interesting. First of all, is that as you are going towards larger group size, you are going further away from the vertical line, meaning that the largest group, which is forming the given group at the given size, is somewhat smaller, not only one. So it's not only one person joined the group, but people are arriving in groups in the larger social group. And this is true for living. People are living in chunks. There's the largest subgroup on average, the largest probability that is going to leave the social. And what is even super cool is that they are symmetric. No reason why they should be symmetric, but they are symmetric. And you can measure it in all the contexts. And you can see even extreme cases that, for example, here or here, where they are getting very far away from the vertical line, meaning that large groups arrive to form a group of a given size, and larger groups leave when it is falling. All right. Now the question is, we have all these observations, the broad distribution of group sizes, the broad distribution of duration of groups, the transition matrix on the individual level, and this group size solving and dissolving symmetric and non-vertical distribution of of the data set that we observe in all the contexts. Now the question, how can we set up a model that reproduces all this? Okay. To do that, we are actually building on a model that was defined by Alan Barat and Gina Sabianconi about 10 years ago, which identified one mechanism. And we are also identifying the second mechanism that we already worked on again about 10 years ago. So we are merging, we are combining knowledge to put this together to explain all this. The first mechanism that we wanted to quantify is the question that if I would like to leave a group, should I leave or should I stay? Okay, so I'm at time t. I have to decide at time t+1 whether I'm going to stay in the group where I am or I'm going to leave the group and do something else. Okay, this mechanism, what's called Schizming. I don't know whether you know this expression. Schizming is the procedure when groups are growing large enough that they are going to fall apart. Schizming is also used in theology. For example, Schizming, I just learned yesterday, when the Orthodox Church, that the Catholic Church, that is the schisming of the Catholicism, set apart. Okay, so we are looking for this schisming mechanism. We are looking for how groups are going to fall apart, how groups are going to break apart. And what we actually also realized, and this idea is coming from the previous studies of Alan Barat and Gina Sabianconi, is that there is a reinforcement mechanism playing a role here, namely that longer you stay in a social group, smaller the probability that you're going to leave it. Okay, so there is a rich gets richer type of, or a long gets longer type of mechanism. It is also true being isolated. Longer you stay isolated in a social environment, larger the probability that you will stay isolated in this environment. Okay? So how can we quantify this? Actually, we could measure this from the data. We could measure the group change probability, so the probability that you are going to change the actual group where you are from, as a function of the duration. And we found that this is actually, I can say about this is a power. This decreases as a power, indicating that longer the duration of a group, smaller the probability that you are going to change it. Okay? We quantify this in this form, where we have this beta exponent describing the decay of this power law, but yet we have this multiplicative decay parameter that we didn't describe so far, but actually we could also measure this data from the data. This is indicating that this dependency, this power of decay, is depending on the size of the social group. Okay? Because larger groups are going to fall apart easier than smaller groups, so there must be a size dependence, that's indicated by K. And we found that this dependence can be well approximated with logistic function. Okay, so we have power law decay of the probability to change a group, which power law decay depends on the group size as a logistic. You can see that the green points are the data, and we could fit a logistic function within the arrow bars. You may find a better functional form to fit there. We choose this because it's easy to handle. Okay? Now, the second mechanism is that once you decide to leave, where do you go? Whether you can become isolated and not join any group, or you can actually join a larger group. But what decides which group to join? And this was actually motivated by some other literature showing that there is a social reinforcement. Again, in this process, you are liking to join groups where you know people. Okay? So it means that the larger the fraction of people who you have already interacted with earlier, larger the probability that you are going to choose this group to join. Okay? How can we measure? Actually, we could measure this again. You could just measure the group selection probability, so the probability that you choose a given group as the function of the fraction of nodes you already know in that given group. And these are the gray bars. You could see that these are strongly concentrated around 1, meaning that with the largest probability, you are going to choose a group where you know the people. Okay? The other two measurements, they are random control measures when you are choosing randomly or when you are choosing randomly of the same size. And they are significantly different than the empirical observation. So this is our second mechanism, that you are actually choosing with a larger probability groups where you know the people, where there are nodes who you have interacted earlier with. This is just a quantificative way of quantifying this into a probability that we can integrate into our model. This is completely parameterless. This is measured from the data. So all in all, we have a model which has the following parameters, which has this pk function describing the probability whether you live. You have the pk logistic function describing how this pk probability depends on the group size, and the rest can be determined from the data. So these are the 4 parameters we need to know. The beta exponent of the decay of this probability distribution. I didn't talk about epsilon. Epsilon is a parameter which determines, which is introduced that you can become isolated. How it works. When you decide to leave a group, it's not necessary that you are joining already existing group, but it's possible that in the next time step you are going to be alone. So this possibility has to be included into the model. And how we do this? We are actually adding epsilon fraction of empty groups that by chance you could choose, which means that with that epsilon probability, you are going to stay isolated, become isolated in the next. Okay, so this is the epsilon number of empty sets to join, meaning that with this probability you will become isolated in the next step. And we have the other 2 parameters characterizing the logistic function. So actually this model can be fit on the group size distribution and the transition matrix. It's just optimization process using KL divergence as a distance between the empirical distributions and model distribution. And what is very surprising that when we fit on this and we measure the 2 other parameters that we observe, what comes out is very similar to what we observe in reality. We observe a somewhat broad group duration distribution, depending in the same way from the group size as empirically. So smaller groups are sticking together longer and larger groups are falling sooner. And we also get back with the best parameterization this symmetric but not vertical distribution of group dynamics, showing that actually chunks of people are joining groups and chunks of people are leaving the groups when the groups are larger, while at the same time, for smaller groups, this is just an increment plus or minus a small number of people are joining or leaving the group. So all in all, this is all I wanted to say. I would like that you remember 3 things. First of all, the DLNet project. This is very important. If you want or you know someone who wants to work on children's speech recognition, please contact us. This is very crucial. And also, I just would like to highlight the 2 mechanisms that we identified that could explain this group dynamics of groups, both in the preschool children and for university class students, university student classes. The short-term memory, the longer the mechanism in terms of long-term memory, this recurring social context, the 2 mechanisms that can explain all what I was talking about. All the data and the results are published in these 3 papers. The first paper is about the temporal network reconstruction. The second paper is about the data that has been shared, and the third one is this group dynamics study that I was showing to you in the end. And well, they are our collaborators. You can find some of them in the group, some of them probably you know. There are 2 groups of people who worked on this project. The first one was Sicheng was my PhD student, Helen Bouchet, who was a postdoc. She's the ethologist who was sitting in the room. Okay. Eric Fleury, who is now in Paris at India, and Jean-Pierre and Morelli, who are sitting in the room. And in the second project, I was working with my postdoc Jacopo Iacopini and Alain Barat to study the group dynamics. And finally, if you would allow me a shameless advertisement, there are 3 things that I would like to advertise. We have a new master program at my department. It's a master program in social data science. So if you are interested, or you probably have passed your master's studies, but if you know someone who is interested in studying data science contextualized around social problems, please don't hesitate to reach or advertise us to them. We have 4 specializations in economics, environmental science, political science, and policy data science. We also have the only PhD program in network science in continental Europe. Now there is one in the UK, that's fine. It's the same as continental Europe. This is a long-running program. Almost we do it since 10 years. It's a 4-year fully financed program. The application deadline didn't write up because it's in February, so probably still have time. I can already address that. It's certainly going to be February. So please tell people who would like to do a PhD in network science to apply. And finally, I happen to be the editor-in-chief of the journal Advances in Complex Systems, which is one of the first complex system journal that was published by, actually it is published by World Scientific, and we are redesigning the journal to host more contemporary complex system science. So if you have papers that you are searching where to publish, don't hesitate to comment. I promise you a better and quick editorial process. That's all I can do. And I think that's it. Thank you very much.
First thing we go. I have a question about the last. So you have a distribution of duration, which is power law. So usually power law decay is cut off by some exponential or something, because you cannot measure very duration. Does this affect your modeling or tiny?
It's not only an observational bias, the exponential cutoff of the duration distribution. It's also because we have a circadian pattern. So no social group is surviving longer than 24 hours. Right? In this context, online certainly does. But in physical context, there is the end of the day when it goes home, there is going to be a cutoff of the length of the duration. It's a very good question. We characterize this as a power law. We didn't consider that it has. Okay? So we just characterize them. We wanted to actually obtain back a similar shape of the duration distribution. In the model, the duration distribution is not given; it is emerged. Okay, so we are not giving any information to the model that it has to be a power law or it has to be distributed in a heterogeneous way. And what we get is this one. So it is emerging as a broad distribution. It is not emerging as a power. As you can see, you cannot really fit a straight line any section of this distribution. It has it's probably more like a stretch exponential distribution, right? But it is broad. And this is what we wanted to get. We did not try to obtain a distribution. We saw that the original distribution has some part which can be corresponding to power distribution. But as an emergent behavior, we got similar broad distribution. Thank you. Any questions?
Maybe I have a question about the group size. In the school, there are these constraints for the class where a certain amount of people are inside the same classroom. And you are not modeling that here, right?
No.
Okay. So what do you think? Can you see is it this effect that you don't have this vertical here?
Well, so by the group size distribution, we are fitting on it. So I didn't show you, but we have this result for all the contexts.
Yes.
And it is an input parameter, the distribution itself. And the distribution cutoff is determining, of course, the size of the emerging groups.
Okay, so it's included in.
Yes, we are fitting on the group size distribution and this transition metric. These are the two things that we take from the data and fit the model on. And what we obtain as an emergent behavior is the duration distribution and this group evolution transition. Online.
I would ask that one. Will you be able to put in the model the language datasets? Or
Yes, that's a very good question. I mean, this model completely disregards any characteristics of individuals, right? And potentially one can introduce the characteristics, whether you call it language or color, or I don't know, height or gender, doesn't matter. You can introduce individual characteristics, meaning that you can introduce bias preferences towards interacting to similar others. And then and we have done this, not with this model, but with other models.
Okay.
You can obtain social groups emerging because of this bias.
Okay.
Not because you are feeding in the group size distribution. So there is a more general model than even the group sizes due to choice preferences or choice bias can
And you can apply also this sort of model to social network like Twitter or X.
Well, the group dynamics is probably somewhat different. There are others. So I have another model, or we have another model that I built with a student in Lyon many years ago, which shows very similar patterns than, for example, online temporal. But it is based on this activity-driven network that I mentioned earlier, where the assumption is that you have a set of nodes, and the only assumption you make is that their activity, meaning the probability that they become connected to someone, is coming from an empirical distribution. And that activity distribution determines the emerging distribution, and then you can introduce this triangle closing mechanism, this choice preferences, and you can get most of the phenomenon which generally characterize all social networks, like clustering, the Granovetter type of weight structure correlations, assortativity, and all this. So you can rebuild, but at the same time, it's a temporal network. So you can, for example, model information diffusion. Epidemic spreading is very easy.
Do you think that the group dynamic may be sensitive to the size of the general population? For example, institutional or playing the payroll from large sensitive people?
Well, if you fit this in, it determines the group size. If you have a other distribution that you observe, for example, in the university classroom context, this goes way higher than 12, and it's 700 kids. They are not in the same classroom, but if you fit that distribution, you will observe larger distribution, larger group size. So it all depends on the context in this modality. Otherwise, it never measures the thermodynamical in models where groups are emerging without. It depends on parameter how cohesive these biases are.
So thank you for the first. So how do you define it? The second question is can present in two groups.
Yeah. So this is it's also a very good question. We assume that no overlapping groups. So one group, one person, one group. And how you define a group is the simplest possible you could do. You assume that the group is a clique. So for example, if I had this 4 click here, and I would miss this link, that would not be a group of 4. Okay, so it's it means that these 4 people mutually detected each other. Of course, the next question could be, how does it depend on the resolution? So for example, the time window size, because now I aggregate it up to, I think, 10 minutes. Okay, so if in 10 minutes these kids mutually play with each other, they form a social group. But what if it's only one? So this is a hyperparameter, I think, which I get in the papers. Yeah.
I apologize for being late. In the classroom setting, do you have a way to distinguish teacher-assigned groups versus naturally evolving groups?
it's recorded in the anthologies
Uh-huh.
who knows exactly what happened.
Okay.
So we know that they are sit around tables, they are left free to play with each other, or they are in the playground. And then they can use the classes. So we have this schedule throughout the day for each. For each class, or only the class that shares. Depends. Yeah, but normally we have.
Just the group dynamics change.
The size, sure. And also the composition. In the homophily study we do, it is certainly visible that, of course, when the kids are sitting around the table, probably the teacher is designing a gender balanced, behavior balanced, you know, that is not a single table around all the troublemakers sitting, you know, it's like, so this kind of homophilic biases or choice preferences, they are lower when they are seated around the table. And when they're free to choose, then it depends. Because, for example, in the class, in the yard, in the playground, these preferences change when they mix with others, even other age groups. So, for example, petite section class is mixed with a grand section class. You can see that how the gender preferences and age preferences changing as their age is going. So in the beginning, there is no gender preference. Older kids, they have gender preference. And you can observe all this evolution of their selection bias. Thank you very much.